Hi folks, my name is John Drake. I'm an assistant professor of tree physiology here at SUNY ESF. And today I want to talk to you about the autumn leaf color change. So here in the northern hemisphere we have this beautiful thing that happens in the autumn where we have a whole community of forests that start with green leaves and they develop this brilliant, wonderful autumn leaf color, including this reds of this sugar maple or the yellow of this hackberry. And so today I want to talk about the physiological processes of why trees are doing this and then how trees are doing this with three pigment classes. We're going to talk about leaf pigments. But the primary reason, the thing that trees are doing is that they are recycling nutrients from their leaves. They're resorbing nutrients and storing them in their bodies before they let their leaves fall in the autumn. And they're primarily interested in recycling nitrogen. For most of these trees, nitrogen is the primary limiting nutrient that is preventing that tree from growing faster and making more fruits and seeds. Inside of this green sugar maple leaf is a whole lot of photosynthetic proteins, ribisco and all the other enzymes that are driving the Calvin cycle, and that there's a lot of nitrogen tied up in those proteins. Those proteins get chopped up into pieces, into amino acids, into their component amino acids. And those amino acids are soluble and can be resorbed from the leaf through the phloem and stored in the phloem and rays within the upper branches of a tree that will help build the canopy up in the next year. And these beautiful colors that trees show in the autumn are a way of protecting this recycling process from the potentially damaging influence of light. This is a light protection process that allows for this recycling to happen. There are three primary classes of pigments in these leaves. You know one of them, the green in these leaves, is from chlorophyll. And I'm going to draw kind of their rough molecular form. This won't be exactly right, but chlorophyll has a head. In that head, it has nitrogen atoms that are holding a central magnesium molecule. And then it has this tail. These are chlorophylls. Those are the molecules that are giving leaves their green color. There's also a whole class of yellow molecules called carotenoids. So there's only two chlorophylls, chlorophyll A and B in plants. There are like 300 different carotenoids. I'm going to draw an example of one of them. This is meant to be a yellow marker. I'm not sure it actually shows up as yellow. And these rings showing the benzene rings here. These are carotenoids. A very famous carotenoid is beta-carotene, one of the primary carotenoids found in carrots. Carrot is a part of this word carotenoid. And so the yellow color that you're seeing in autumn leaves is primarily you're seeing the influence of the carotenoids. So these pigments are not just floating around in leaves. They are held in these three-dimensional structures called light harvesting complexes that are held together. So the chlorophyll and the carotenoids are core components of the light harvesting apparatus of photosynthetic leaves, and they are always held together. So this green leaf has a whole bunch of yellow carotenoids in it that you can't see. The green is essentially masking the yellow color of the carotenoids. Now, for a leaf that's recycling all these photosynthetic pigments, it's actually all these photosynthetic proteins to get the nitrogen into these stored amino acids. If chlorophyll kept absorbing light and kept doing electron transport through photosynthesis, it could lead to the damage of these proteins, right? So we actually want to, leaves seem to reduce their light absorption, reduce the potential photo damage they would get from light absorption as a process that enables the retranslocation of proteins. So the first thing that leaves do is they break this bond here and break down this tail that holds chlorophyll into its light harvesting complexes, and they get rid of this magnesium atom in the head of chlorophyll. And they do not recycle the nitrogens from this the chlorophyll's head. This structure gets chucked away in the vacuole of leaves, which is kind of like the storage area. You can think about it as like a big warehouse. And so this gets stored in the vacuole. It's now colorless, it's no longer absorbing light, and it's not generating electrons through the electron transport chain. So when a leaf goes from green to yellow, it is because of the loss of chlorophyll, and you're now seeing the yellow pigment of the carotenoids that were already there. So the yellow color that is common in lots of trees. I have a ginkgo across the street from me that turns a really brilliant yellow every year, and that is, we are now seeing the carotenoids that were already there. There's another class of pigments that some plants make called anthocyanins. And I'm going to try to draw this in red. Here's an oxygen. There's 2 rings there, and there's a ring there. You don't need to know these particular structures, but you need to know that there are different pigments in plants that have different molecular structures that give them those colors. And these are called anthocyanins. And there's a bunch of these. And if they're responsible for the violets and the purples and the reds of fruits and flowers and leaves. This chemical is not always present in leaves. Most leaves don't have substantial amounts of anthocyanins. They seem to be made and created de novo, newly created in the autumn in some plants. And so here is a red sugar maple leaf. So this tree was transitioning from green leaves primarily to red leaves. So at the same time that this tree is breaking down its chlorophyll and inactivating its chlorophyll, it is making another chemical called anthocyanin that gives leaves these red colors. I want you to think of anthocyanins as sunscreen. If we don't want to get sunburned, we rub sunscreen on our body. That sunscreen blocks solar radiation and prevents it from going into our skin and causing photo damage of our skin. These anthocyanins also absorb light energy from the sun. It is safely dissipated and doesn't cause photo damage in leaves. And so the red color that you're seeing in the anthocyanins is like this leaf is putting on sunscreen to reduce the amount of light energy that it is absorbing so that it can safely do the recycling of proteins. This might help you explain some of the patterns of the changing colors that you observe. You primarily will observe, particularly if you're looking at like street trees in the city, you'll see color developing first at the top of trees' crowns, and particularly in sunlit branches that might be extending over a road or into a gap. Those will change color first and often most vibrantly as we have photoprotective mechanisms in those leaves that are protecting them from photo damage while they are resorbing all of this very valuable nitrogen that's in their photosynthetic proteins. So the nutrient resorption is primarily not coming from the pigments. Plants are not getting the nitrogen back from chlorophyll. They're getting the nitrogen back from the resorption of the nitrogen in their photosynthetic proteins, and that is enabled by changes in these 3 pigments. Thanks very much for your attention. I hope you learned some about the